Hey guys, we are starting a new chapter. So yesterday we went over the chapter opener and we talked, just about some of the vocabulary. This is a larger, more dense chapter on quadrilaterals. But we're starting with section 1. We're talking about angles of polygons, both interior and exterior. We've got a lot more vocabulary and it's going to be a bigger chapter. So the objective of the first section is simply to use the interior angle measures of polygons, any polygon, and the exterior angle measures of polygons. So we'll break that up into two parts and look at all these vocabulary that we should know. We're going to be learning diagonal, equilateral polygon, equiangular polygon, regular polygon, and that regular doesn't just mean normal. Regular means all the same sides and same angles. Previously, you should remember polygon, convex, interior angles, and exterior angles. So let's get started. We're going to talk about these interior angle measures of the polygons with these pictures. So first, in a polygon, two vertices that are endpoints of the same side are called consecutive vertices. So consecutive means one right after the other, like 1, 2, 3, 4, 5 are consecutive numbers. A diagonal of a polygon is a segment that joins two non-consecutive vertices. So A and B doesn't count, but A to C, that would be a diagonal. Or B to D, that's also a diagonal, but B to C or B to A is not. As you can see, the diagonals from one vertex divide a polygon into triangles. Dividing a polygon with n sides into n minus 2 triangles shows that the sum of the measures of the interior angles of a polygon is a multiple of 180 degrees. So when you make the first triangle, you use up 2 of those sides. And then you only need one more to use up another one and one more to do another one. So there are 1, 2, 3, 4, 5 sides. So if n is 5, it makes 3 triangles, which is 2 less. We'll go over that in class as well. So we've got one theorem. First of all, the Polygon interior angles theorem. And here it is. The sum of the measures of the interior angles of a convex n-gon, okay, so we'll talk about what that means too in class, is n minus 2 quantity times 180 degrees. So in this one, if n is 5, n minus 2 is 3, there are 3 triangles of 180 degrees each, and so 3 times 180 is 540. So for this one, if n equals 6, then n minus 2 is 4. From there, we're going to do times 180 degrees, and that's going to give us 720. Remember, a polygon is convex when no line that contains a side of the polygon contains a point in the interior of the polygon. I always think of it as it's going outward. Okay, there's no place where it goes inward on itself. So that would be concave. So if you want to see more a proof of this, in example 42 for pentagons is in your book. We're just going to keep going with vocabulary and concepts. So here's an example where if you want to find the sum of angle measures in a polygon.
Find the sum of the measures of the interior angles of the figure. Solution. The figure is a convex octagon. It has 8 sides. Use the Polygon interior angles theorem. By this theorem, the sum of the measures of the interior angles of a convex n-gon is the quantity n minus 2 times 180 degrees. Because the figure has 8 sides, substitute 8 for n. Now subtract. 8 minus 2 is 6. Then multiply. 6 times 180 degrees equals 1080 degrees. So, the sum of the measures of the interior angles of the figure is 1080 degrees.
If I were going to draw on this, and I drew from one vertex to all the other vertices, I would get 6 different triangles, and each triangle has 180 degrees. Monitoring progress, we'll do that in class. Here's another example of finding the number of sides of a polygon.
The sum of the measures of the interior angles of a convex polygon is 900 degrees. Classify the polygon by the number of sides. Solution. Use the Polygon Interior Angles Theorem to write an equation involving the number of sides n. Then solve the equation to find the number of sides. By the Polygon Interior Angles Theorem, the sum of the measures of the interior angles of a convex n-gon is the quantity n-2 times 180 degrees. You know that the sum of the measures of the interior angles of a convex polygon is 900 degrees. So, by the Polygon Interior Angles Theorem, you can write the equation, the quantity n-2 times 180 degrees equals 900 degrees. Now, to solve for n, first divide each side of the equation by 180 degrees. This gives you n-2 equals 5. Then add 2 to each side of the equation. This gives you n equals 7. So, the polygon has 7 sides. It is a heptagon.
There are lots of names of different polygons. 7 is for hepta. So now we're going to move on to a corollary. So the sum of the measures of the interior angles of a quadrilateral, and only a quadrilateral, is 360. Because if something has 4 sides, and n is 4, then n-2 is 2, and 2 times 180 is 360. There is a proof again in your book, for example 43, but hopefully you can see that anytime you cut something up that has 4 sides, you're going to end up with 2 triangles. Here's an example where you're going to find the unknown interior angle measure.
Find the value of x in the diagram. Solution. The polygon is a quadrilateral. Use the corollary to the Polygon Interior Angles Theorem to write an equation involving x. Then solve the equation. By the corollary to the Polygon Interior Angles Theorem, the sum of the measures of the interior angles of a quadrilateral is 360 degrees. So you can write the equation x degrees plus 108 degrees plus 121 degrees plus 59 degrees equals 360 degrees. Next, combine like terms on the left side of the equation. This gives you x plus 288 equals 360. To solve for x, subtract 288 from each side of the equation. This gives you x equals 72. So, the value of x is 72.
Hopefully you followed all that. We're going to do one more example. Before we do, we're going to go over 3 terms. In an equilateral polygon, all sides are congruent. In an equiangular polygon, all angles in the interior of the polygon are congruent. So you can see how all of those angles are the same. However, if we want both equilateral and equiangular, we use the word regular. Okay, so regular polygon. It could be a triangle, a square, a hexagon, any type of polygon with both congruent sides and congruent angles is a convex polygon that is both equilateral and equiangular. That one word, regular, means both. So it's really important that you remember that because it's something that you would normally not think about. So this is a specialized vocabulary in geometry. So here you go for the next example, number 4.
A home plate for a baseball field is shown. Part A. Is the polygon regular? Explain your reasoning. Part B. Find the measures of angle C and angle E. Solution. Part A. A regular polygon is a convex polygon that is both equilateral and equiangular. The polygon is not equilateral or equiangular. So, the polygon is not regular. Part B. First, find the sum of the measures of the interior angles. By the Polygon Interior Angles Theorem, the sum of the measures of the interior angles of a convex n-gon is the quantity n-2 times 180 degrees. The polygon is a convex pentagon. It has 5 sides. So, substitute 5 for n. Now, 5 minus 2 is 3, and 3 times 180 degrees equals 540 degrees. So, the sum of the measures of the interior angles is 540 degrees. Then write an equation involving x and solve the equation. Let the measures of angle C and angle E be x degrees. Then, because the sum of the measures of the interior angles is 540 degrees, you can write the equation x degrees plus 90 degrees plus 90 degrees plus 90 degrees equals 540 degrees. Next, combine like terms on the left side of the equation. This gives you 2x plus 270 equals 540. Now solve for x. First, subtract 270 from each side of the equation to get the equation 2x equals 270. Then divide each side of the equation by 2. This gives you x equals 135. So, the measure of angle C equals the measure of angle E, which equals 135 degrees.
Again, hopefully you followed all that. Now we're going to go to the second part of the lesson. Not only are we going to look at interior angles, we're also going to look at exterior angles. So, hold your hat. Let's get ready for this. One more theorem and then 2 more examples. Here we go. Oh, that's monitoring progress. Okay, so using exterior angles. Sorry, pressed the wrong thing. Now, around the outside, that's the exterior of a polygon, it's always 360. Always, always, always 360 degrees. So it's a little easier concept to figure that out, but let's just read it. Unlike the sum of the interior angle measures of a convex polygon, the sum of the exterior angle measures does not depend on the number of sides of the polygon. The diagram suggests that the sum of the measures of the exterior angles, one angle at each vertex of a pentagon, is 360. In general, this sum is 360 for any convex polygon. Super important, any convex polygon. And there's some examples here. You can see that if you add all of them together, you're going to get 360 degrees. This is just how you would do that. Now that leads us to a theorem, which is the Polygon Exterior Angles Theorem. The sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. So as you can see here, this is a pentagon where n equals 5. If you add the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 plus the measure of angle 5, you're going to get 360 no matter what. If it's a hexagon with 6, it would be all that with 6. There's the example 51 is the proof in your book. So let's look at how this works. Example 5.
Find the value of x in the diagram. Solution. Use the Polygon Exterior Angles Theorem to write and solve an equation. By the Polygon Exterior Angles Theorem, the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. So you can write the equation x degrees plus 2x degrees plus 89 degrees plus 67 degrees equals 360 degrees. Next, combine like terms on the left side of the equation. This gives you 3x plus 156 equals 360. Now solve for x. First, subtract 156 from each side of the equation to get the equation 3x equals 204. Then divide each side of the equation by 3. This gives you x equals 68. So the value of x is 68. If
you did then plug in 68 here and 136 here, which is twice that much, and added them all together to check, you would get 360. Here's another example, and we'll wrap up.
The trampoline shown is shaped like a regular dodecagon. Part A. Find the measure of each interior angle. Part B. Find the measure of each exterior angle. Solution. Part A. Use the Polygon Interior Angles Theorem to find the sum of the measures of the interior angles. By the Polygon Interior Angles Theorem, the sum of the measures of the interior angles of a convex n-gon is the quantity n-2 times 180 degrees. Remember that a dodecagon is a polygon with 12 sides and 12 vertices. Because the polygon has 12 sides, substitute 12 for n. Now, 12 minus 2 is 10, and 10 times 180 degrees equals 1,800 degrees. So, the sum of the measures of the interior angles is 1,800 degrees. Then find the measure of one interior angle. A regular dodecagon has 12 congruent interior angles. Divide 1,800 degrees by 12. 1,800 degrees divided by 12 equals 150 degrees. So, the measure of each interior angle in the dodecagon is 150 degrees. Part B. By the Polygon Exterior Angles Theorem, the sum of the measures of the exterior angles, one angle at each vertex, is 360 degrees. Divide 360 degrees by 12 to find the measure of one of the 12 congruent exterior angles. 360 degrees divided by 12 equals 30 degrees. So, the measure of each exterior angle in the dodecagon is 30 degrees.
Hopefully you can follow all that. And then for each one, at each vertex, just a hint, the interior angle and the exterior angle might add up to 180. So that's just about it for section 1. There's a lot of exercises, and we're going to be going over those together. You'll also be expected to know the names of a few of the more common polygons, like pentagon and quadrilateral, hexagon, and octagon. You probably already know a bunch of them with the prefixes that you've talked about before, but we will definitely be going over them in class. So when you see dodecagon, you know that that means 12 sides. When you see icosahedron, you'll know that that means 20 sides. So you will be expected to know them. You won't always be given to you. All right. So for now, we're going to be done with our video, and we're going to start doing examples under the camera.